Here is one of the digital images that we've just been looking at, and on the right we can see some of its pertinent details. Now we can determine the total number of bytes in the image by multiplying the image width by the image height by 3. And the number 3 comes from the fact that for every pixel in the image we need to represent the amount of red, green and blue, and each of those is represented by a single byte. And when we compute this product, we see there's something like 21 million bytes of information in this image. However, on disk, the image only occupies 3.7 megabytes. So the number of bytes on disk is way less than the number of color pixels that there are in the original image. If we take the ratio of these two numbers, we see that the number of bytes required to store the image in the file on disk is a very small fraction of the total number of bytes required to represent all the colored pixels in the image. And this comes about because this image has been compressed. Now all images contain a large number of pixel data, and we want to make the file size as small as we possibly can. That means then we can fit more images into the same amount of disk. There are two fundamentally different approaches to image compression. The first is lossless compression. And what this does is exploit redundancy or recurring patterns in the image and codes them very efficiently, so they require overall less space. And this is in stark contrast to lossy compression, the most common example of which is JPEG compression. And what lossy compression does is exploit the fact that the human vision system is far from perfect, and that there is some information that you can remove from the image in such a way that the human observer doesn't notice very much change. So some of the problems with the human vision system is we're not very good at noticing very fine detail. We're not as good at resolving the differences between colors as we are at resolving the differences between different intensities. And our color sensitivity actually depends on the sorts of colors that we're looking at. So we can exploit these bugs in the human visual system in order to remove information that we wouldn't notice anyway and make the files much smaller. Here's an image of our favorite robot, and on disk this image occupies 480 kilobytes. If we observe this little region within the robot and we zoom in on that, what we can see is that it looks pretty good. We can see the edges are fairly sharp, and there is some interesting color gradations there. Now this image has only been modestly compressed. It's 82% of the original image size. But if we start to increase the amount of compression, we're throwing away additional information, we see that the image starts to become quite seriously degraded when we zoom in and look at it very closely. So with a very high level of compression, the image is only occupying 12% of the original storage. So we've made massive savings in the disk space required, but the image is starting to look fairly poor when we zoom in on it. And if we zoom in even further, we can see that it's become quite blocky, quite quantized, and there are many fewer colors here than there are in the original image. All of these images have the same number of pixels, but the actual file size varies. This image, as we mentioned before, is 3.7 megabytes long. This crocodile is only 2.9 megabytes long. The bird picture is 3.8 megabytes. The size of an image after it's been compressed is a function of how much information is in that image.